I'm Amrita from Department of Electronics and Communication Engineering, and my Tech Talk topic for satellite communications is a taxonomy for neural memory networks. Introduction to neural memory networks. Neural memory networks are models designed to enhance the ability of neural networks to store and retrieve information. They mimic aspects of human memory systems to improve learning and reasoning capabilities. This presentation explores a comprehensive taxonomy categorizing various neural memory architectures. Motivation for neural memory networks. Traditional neural networks often struggle with long term dependency management. Memory augmented models aim to address issues like catastrophic forgetting. Developing a taxonomy helps clarify the landscape of existing memory network approaches. Basic components of memory networks. Memory modules serve as repositories for storing information over time. Read and write mechanisms enable interaction with stored data. Controllers coordinate memory access based on input data and task requirements. So, in the right side, we can see the taxonomy, and these are the taxonomy deals primarily with the description, identification, and nomenclature and classification of organisms. So these are the classification of organisms based on the taxonomy. First one species, second one is genus, third one is family, fourth order, fifth class, sixth phylum, seventh is kingdom, and eighth is the domain. Categorization criteria for memory networks. The taxonomy considers memory structure, access methods, and learning algorithms. It distinguishes between differentiable and discrete memory mechanisms. These criteria help classify models based on their architecture and functionality. Discrete neural memory models. Discrete memory models involve non-differentiable access mechanisms. They often require reinforcement learning or other specialized training methods. These models can mimic more symbolic or logic-based memory processes. So here we can see the discrete neural memory models. This to the address content. Memory structure will be the two types. First external and second embedded. So let us know about the difference between the external and embedded. External memory is separate from the main neural network like a separatable module. Whereas the embedded memory integrates memory components within the neural architecture. The choice impacts flexibility, efficiency, and scalability of the network. So, in the right side, the picture, we can see the memory structure, external memory, and the embedded memory. So, in the external memory and system, there is the interaction between the memory and system. Whereas here in the embedded memory, the system and memory will be within the neural architecture. Access mechanisms: content based versus location based. Content based addressing retrieves memory based and on the similarity to a query, whereas location based addressing accesses memory via explicit position indices. Combining both mechanisms can enhance retrieval accuracy. Memory update strategies. Write operations can be overwriting, appending, or selective updating. Some models employ learned gating mechanisms for dynamic memory control. Efficient update strategies are crucial for long term memory retention. Architectures of neural memory networks. So, the key architectures include neural tuning machines, memory networks, and transformers. Each architecture offers unique approaches to memory storage, and their design choices influence the network's capacity and application scope. Neural Turing Machines (NTMs). NTMs combine a neural network controller with a differentiable memory matrix. They can perform algorithmic tasks like copying and sorting. NTMs emphasize flexible read or write operations for complex reasoning. Memory networks (MNETs). So, these memory networks utilize a fixed size memory and multiple hope attention mechanisms. They excel in question answering tasks requiring reasoning over facts. MemNets often incorporate a static memory component with learned attention. Differentiable neural computers (DNCs). DNCs extend NTMs with improved memory addressing and management. They incorporate advanced structures like linkages for sequential data. DNCs facilitate complex data structure manipulations and reasoning. Transformer based memory models. Transformers employ self attention mechanisms to access information dynamically. They can be viewed as implicit memory systems with flexible access patterns. Recent adaptations integrate explicit memory modules for enhanced reasoning. Hybrid memory architectures. Hybrid models combine differentiable and discrete memory components. They leverage the strength of both approaches for improved performance. Hybrid architectures are promising for tasks requiring symbolic reasoning. Challenges in neural memory networks. Memory capacity and scalability remain significant issues. Balancing differentiability with interpretability is complex. Efficient training of large scale memory models continues to be a research focus. Applications of neural memory networks. They are used in question answering, dialogue systems, and reasoning tasks. Applications extend to robotics, natural language understanding, and decision making. Memory networks enable models to utilize context effectively over long sequences. Future directions and research trends. Developing scalable, interpretable, and efficient memory models is ongoing. Integration with other AI paradigms like reinforcement learning is promising. Advances in hardware may further enhance the capabilities of neural memory networks. Summary of the taxonomy. The taxonomy categorizes models based on memory structure, access, and learning methods. It highlights the diversity of approaches from differentiable to discrete memories. Understanding this taxonomy aids in selecting and designing appropriate models for specific tasks. Thank you.